Assalamualaikum and greeting to all of you. So today we will proceed on the lecture 3 of the attributes and 3D visualization course on the phase and polarity. So this topic is very important, especially for the introductory part to be discussed so that geologists, geophysicists or even seismic interpreter aware the application and the usage of phase and polarity in early interpretation stage for determining the behavior of wavelets towards the subsurface. So as for today's lecture, we will deliver two CLO of this course, which are CLO 1 and CLO 2. CLO 1 is about apply all type of seismic attributes to meet the purpose of subsurface data interpretations, while CLO 2 is analyzing and interpreting the result from seismic attribute applications on subsurface data. But as for the today's topic, we will be more on the concept and the importance of phase and polarity when we discuss about the applications in seismic attributes particularly. So we go a little bit on introductions. So why phase and polarity is very important. So before we go a little bit further, so we need to understand the behavior of the amplitude reflection. So basically, high amplitude reflection on seismic images are caused by a strong contrast in acoustic impedance or AI. So AI is a measure of how easily sound wave can travel through a material. So to identify high amplitude reflections, geologists can look for bright areas on seismic images, so they can also measure the amplitudes of reflection and compare it to amplitude of other reflections on the image. Once a high amplitude reflection has been identified, we geologists can try to understand its geological cause. So this can be done by considering the lithology, fluids, and structure of the subsurface. So it is also important to understand whether the reflection is caused by a single interface or a layer. So a single interface reflection is likely to be caused by a boundary between two different rock formations. A layer reflections, on the other hand, is likely to be caused by a layer of rock that is sandwiched between two other layers of rock with different AI values. So what I want to say is high amplitude reflection on seismic images are caused by strong contrast in acoustic impedance. So we will discuss about acoustic impedance on the next slide. So the diagram on the left illustrates the different sources of seismic reflections that are typically strong enough to be useful for interpreting phase informations. So phase information is basically a measure of the timings of a seismic reflection, and it can be used to identify different type of rocks and geological features. So basically all the features here has a potential indications for determining the information phase. For example, top of salts is a good reflector because the acoustic impedance contrast between salts and the surrounding rock is typically very high. However, the top of salts may not be smooth enough to produce a strong reflections, and the contact between salts and the surrounding rock may be gradational. So this means that the phase of the reflection from the top of salts may be vary depending on the locations, meaning that it's not a continuous reflectors. And water bottom is a reflector, but is often unreliable because it's not a single interface. So the water bottom is typically a gradual transition from water to the sediments, meaning that from the liquid phase to the solid phase. So and this can be cause the phase of the reflection from the water bottom to vary depending on the locations. Hydrocarbon reservoir like shallow gas and igneous intrusions are also excellent reflector because the acoustic impedance contrast between these materials and the surrounding rock is typically very high, and this means that the phase of the reflection from these features is typically very consistent. And reflection termination, for example, like here, or unconformities are always helpful in isolating the character from the geological features. under study because they represent sharp boundaries between different rock formations. So this means that the phase of reflections from these features is typically very consistent. So basically, depending on how good is the data, it will lead you in choosing and also determining the correct information of phase. So seismic polarity is the science of a seismic reflection, and it is determined by the acoustic impedance contrast between the two materials that are causing the reflections, meaning that the top layer and also the bottom layer contrast. So positive polarity means that the reflection is a peak. So this is caused by an increase in acoustic impedance, while negative polarity means that the reflection is a trough. So this is caused by a decrease in acoustic impedance. So the image here shows that there are two main types of seismic polarity conventions. One is American polarity and another one is European polarity. So North American conventions is the convention that is used by almost 50% of the world, but preferred in America and also Canada. So in this convention, a positive reflection coefficient corresponds to positive polarity reflections, while negative reflection coefficients corresponds to negative polarity reflection. So this is kind of normal or in lines in terms of the polarity. And then we also have European polarity. So this convention is used by another half of the world, and it is preferred convention in Europe and also Australia. So in Shell or in this convention, Europe convention, a positive reflections coefficient corresponds to a negative polarity reflections, while a negative reflections coefficient corresponds to positive polarity reflection. So this is kind of reversals in terms of the polarity compared to the American polarity. So understanding the phase of the wavelet give importance to understand ataupun in understanding the polarity. For seismic data processing, polarity convention can be confusing, and in addition to the needs to introduce color display in the use of color. So in presenting and interpreting using colored sections, the critical issue is to communicate the polarity and the use of color for the data. So it is not so important when convention is used because peak and trough are both visible on the color display. So in general, American polarity is preferred in the Americas and also Canada, but it's not necessarily universal in in this region. European polarity, meanwhile, is also preferred in Europe and worldwide, but again, it is not necessarily universal. So this is another example of polarity determinations based on different regions. So for example, on the left, we have the top and base gas sand, which is shown as an increase in impedance red in color in European polarity. While for the American polarity, it is in blue in color when it comes into increase in impedance for the top basement. So for this event, from these two events, we can actually identify which type of conventions that the data is actually used. So we're going to discuss about the three type of common wave phases, which are maximum phase, minimum phase, and also zero phase. So a maximum phase is a wave in which the energy is concentrated at the end throughout the wave, or we call it as end loaded, as shown in this figure. So because of that, the maximum phase has the late peak amplitude and has the higher peak than trough at the back of the of the wavelet. And then we move into the minimum phase. So a minimum phase is a wave in which the energy is concentrated at the beginning of the wave. So this means that the peak of the wave has higher amplitude than the trough at the early stage. Zero phase, meanwhile, so zero phase is a wave, or we call it as a linear wave, in which the energy is distributed evenly throughout or constant, uniform throughout the wave, and the peak is in the middle, meaning that it is centralized between two low amplitude of trough. In terms of build-up rate, the build-up rate of a wave is the rate at which the amplitude of the wave is actually increases. So minimum phase has the fastest build-up rate, followed by a maximum phase, and then followed by zero phase. In terms of the applications, so a maximum phase is used in variety of application, basically, such as time to depth conversion in seismic data processing, while a minimum phase is widely used for deconvolution processes, and zero phase is used for visualizations and also interpretations. So generally, all the type of all type of phases has their own function and usage, especially in seismic data processing, for minimum and also maximum phase. So while for the zero or linear phase is commonly used for seismic data interpretations and visualizations and also attribute analysis. So basically, phase is very important in seismic data because it allows us to accurately locate seismic event and to produce high resolutions images of the subsurface. We go with the number one why phase is important, which is acquisition delay. In seismic acquisitions, there is always delay between the firings of the seismic source, for example, air gun and also vibrator, and the arrival of the seismic wave at the receiver. So this delay is caused by a number of factors, including the distance between the source and receivers, which is what we call it as offset, and the propagation velocity of the seismic wave and the response of the seismic equipment. Number two is because of the correct phase. So correct phase in seismic data means that the seismic event are positioned accurately in time and space or distance. This is important for a number of reasons, including number one, accurately locate the seismic event or the seismic source, and number two is to produce high resolution images of the subsurface. And then next we have zero phase. So a zero phase seismic data, as we discussed earlier, is the data that has been processed to remove all phase shift. So this is the ideal type of seismic data for most applications, as it gives the most accurate representation of the subsurface. However, it is important to note that zero phase in seismic data is not always possible to achieve in the real world, because the positions of the receiver and also the source cannot be in the same locations and same place in reality. And then we also have resolutions. So in terms of resolutions, phase also plays an important role in seismic resolutions. So the resolution of a seismic image is determined by the length of the seismic wavelets. A shorter wavelet length results in higher resolutions. Phase can be used to compress the seismic wavelet and to improve the resolution of the seismic images. And then we also have phase conversion. So phase conversion is the process of converting seismic data from minimum phase to zero phase. So minimum phase data is the data that has been processed to remove all phase shifts that are caused by the seismic source and the seismic equipment, while the zero phase data is the data that has been processed to remove all phases shift. So, and then we have the final one why phase is important, which is the mixed phase. So the mixed phase seismic data is the contents of the mixture of zero phase and also minimum phase data. So mixed phase data is often used in seismic interpretation because it can be easier to interpret than zero phase data. However, it is important to be aware of the potential error that can be introduced when using mixed phase data. Okay. Overall, phase is important property of seismic data that affect the accuracy and resolution of the seismic images. By understanding the importance of phase, we can be better. We can have a better process and interpret seismic data to gain valuable insights into the subsurface. So zero phase seismic data is preferred because it has a number of advantages over other type of seismic data or seismic wave phases, including number one, wavelet symmetry. So zero phase wavelets are symmetrical with the majority of the energy concentrated at the central lobe. For example, over here in the blue color. So this wavelet shape minimize ambiguity in associating observed waveform with subsurface interfaces. And then we also have a central lobe energy. So this central lobe energy, which is in the red color over here, is maximized, which allow for more accurate horizon tracking and amplitude analysis. And then we also have a horizon track. So a horizon track drawn at the center of zero phase wavelet, meaning that at the peak of the coincides in the time with the travel times to the subsurface interfaces, causing the reflection. So this is because the central lobe of a zero phase wavelet represent the peak of the seismic response. And then next we also have maximum amplitudes. So zero phase is important because the maximum amplitude of the zero phase wavelet occurs at the center of the waveform and thus coincides with the time horizons. So this makes it easier to identify and track horizon in seismic data using the zero phase wavelet. And then we also have the resolutions. In terms of resolution, zero phase wavelet have better resolutions than other type of wavelets with the same frequency content. So this is because zero phase wavelet are less dispersive, meaning that they do not spread out as much over times. So overall, zero phase seismic data is preferred because it produces more accurate and higher resolution images of the subsurface. And in addition to the advantage listed above, zero phase seismic data is also easier to process and interpret other than type of seismic data, particularly for the minimum phase and also maximum phase, or even for the mixed phase. So this is because zero phase wavelet are more stable and less prone to noises. And then while zero phase seismic data is not always possible to achieve in the real world, it is the goal of the seismic data processing to get as close as possible to zero phase. So this is important for processing high quality seismic images that can be used to accurately interpret the subsurface. So in terms of wavelet phase shapes, all these wavelet have an identical amplitude spectrum. The only difference is that they have a different phase spectra. So seismic source tend to be close to minimum phase. It is a zero phase wavelet that gives the best resolutions for any given amplitude spectrums. One of the aim of the seismic data processing is to generate sections that are zero phase and with large bandwidth like here. So how to check your data phase and polarity? So to check your data phase and polarity, basically we go from step to step. Number one, we need to identify a high amplitude reflection, which can be assumed to originate from a single interface. So this could be a fluid contact reflections or flat spot as an example. And then we need to display data in color. So black and white is very difficult, but we need to display in color because it will give you a brighter spots, and this will allow you to see the polarity of the reflections. And number three, you need to observe the polarity of the reflections. So if the reflection is red, then the data are European polarity, and if the reflection is blue, then the data are American polarity. So if the reflection is symmetrical, then the data are zero phase, and if the reflection is not really symmetrical, then the data probably not zero phase. In this example, for example, the flat spot is red symmetry at this part, so this indicate that the data are zero phase and a European polarity. So the image shows a diagram of different type of gas related bright spots. So the bright spot is one of DHI, or direct hydrocarbon indicator, that are caused by the reflections of wave from different layers of rocks and gas, regardless either European or American zero phase. So the different type of bright spots are depending on a depth of sediments burials, and also the content in the reservoir, either fluids or other than fluids. They are commonly in normal gas related bright spot, gas related bright spot with phase reversals, and also either hard ground related bright spot. So let's take a look on the normal gas bright spots. So in this case, where gas is not presented in the reservoir that has been sandwiched by the shell units, the AI will be low at the reservoir interface because sand commonly has high porosity. This will give low density and low AI. However, the reservoir has, if the reservoir has a presence of a gas, then AI or acoustic impedance will even decrease more at the reservoir and increase the contrast of AI with the surrounding shale, which create high amplitude response, which create the bright spots. So this is the most commonly type of bright spot that is caused by the reflection of wave from a layer of gas bearing sand. So the bright spot is bright because the acoustic impedance AI of the sand is lower than the acoustic impedance of the surrounding shale at shallower subsurface, or shallow subsurface. So this is the case in the shallow subsurface. So what happened when we have at deep subsurface with the same conditions? So the gas related bright spot with phase reversal will be happening in deep subsurface, where sand reservoir will have slightly higher. If you look over here, it will higher in term of AI due to a better compactions and also cementation compared to the above scenario. However, when the presence of gas in the reservoir is happening, again it will lowering the acoustic impedance of the sands layer compared to the surrounding shales, resulting a phase change at the gas bearing sand. Similarly, like before, the bright spot is bright because the acoustic impedance of the sand is lower than the acoustic impedance of the surrounding shale at shallow subsurface, but this one will be in the deeper subsurface. And then we also have hard ground related bright spot. So this type of bright spot is caused by caused by the reflections of the wave from a layer of hard ground, such as shale bed. So the bright spot is bright because the acoustic impedance of the hard ground is higher than acoustic impedance of the surrounding shales. So overall, these diagrams shows the stratigraphy of the rocks, which is uh, the order in which the rocks were deposited. Okay, at the shallow part we will have a gas related bright spot. At the deeper sections we will have a kind of phase reversals. So the stratigraphy is important for understanding the distributions of the bright spot, because the bright spots are only present where there is in contrast in acoustic impedance between the different layer of rocks. So we already went through the concepts and also fundamental of phase and polarity. So why don't we go with the history of phase and polarity? So the history of phase and polarity in seismic attributes can be traced back to the late of 1960s to early 1970s, when Nigel Anstey was working as a contractor on acquisitions and seismic data processing. At that time, the first seismic attribute was reflection amplitudes, which was used to identify bright spots in the seismic data. So Anstey was excited by the potential of a bright spot, but he found that the direct identification of bright spots in seismic data was difficult due to the reflection character. So he discovered that he could highlight bright spots better by displaying a crude measure of the trace envelope, which he called reflection strength. So reflection strengths remove differences due to polarity and phase from seismic amplitudes, rendering bright spots more visible and permitting fairer comparison between amplitude anomalies. So Einstein was also one of the first to successfully display attributes in color and overplotting them with the original seismic data in a variable type of format. So this made it much easier for interpreter to visualize and analyze seismic attributes. And still works on reflection strength, and the display of seismic attribute paved the way for the development of more sophisticated seismic attributes such as instantaneous phase, instantaneous amplitude, polarity, instantaneous frequency, and many more. So these attributes are now widely used for seismic interpreter to identify and map geological features such as lithology, fluids, and porosity. So the importance of phase and polarity in seismic attribute is that they can provide valuable information about the geological features that are generating the seismic reflection. For example, phase can be used to identify discontinuity in the seismic data. So that's why phase attributes sometimes or commonly known as continuity attribute types. So it will detect such geological features like faults and also pitch out. Polarity can be used to identify the type of geological boundary that is generating reflections such as AI, contrast, or fluid contacts. So in terms of application of phase and polarity, so number one, it can be used for interpretation of the seismic data. So phase and polarity can be used to identify different type of seismic events such as reflection, refractions, and also multiples. This is because refractions, and also multiples have a different phase and polarity characteristics. And then it can be used for velocity analysis. Phase and polarity can be used to estimate the velocity of seismic wave in different part of the subsurface, because the phase and polarity of the seismic event changes as the velocity of the seismic wave changes. And then it also can be applied for stratigraphic analysis. So phase and polarity can be used to identify different stratigraphic unit in the subsurface, because different unit of stratigraphy often have a different phase and polarity characteristic. For example, a sandstone layer may have a different phase and polarity phase and polarity than shale layer. And then we also can use to for reservoir characterizations, where phase and polarity can be used to characterize the reservoir properties such as porosity and also permeability. So this is because the phase and polarity of a seismic event is affected by the reservoir properties. For instance, a high porosity reservoir may have a different phase and polarity than low porosity reservoir. So there are actually many type ataupun common type of phase attribute that we will discuss throughout this semester. And the most common attributes are instantaneous phase attributes, phase coherent, and also phase curvature attributes. So we will go one by one in general in the next slide. Now, let's take a look on the instantaneous phase first. So, instantaneous phase is calculated using a Hilbert transform. So, the Hilbert transform of a signal is a complex signals that contain the phase informations of the original signals. So, the instantaneous phase of the seismic wave can be calculated by taking the argument of the Hilbert transform of the seismic wave as shown in these equations. So about the Hilbert transform in particular, we will have explanations or discussion in the next chapter. So the instantaneous phase of the signals in this graph, is shown by the red line. So the instantaneous phase is 0 at the peak of the signals and 180 degrees at the trough of the signals. So the instantaneous phase change linearly between the peaks and the trough of the signals. So the phase is read either positive or negative regardless the value of the amplitude, but differ in the time domain based on the frequency. Meaning that the instantaneous phase is read the amplitude phase but not its value, and the phase was controlled by the frequency. For example, over here, okay, regardless the value of amplitude, the phase will be similar. So this one we have a low amplitude with the same phase that we have high amplitudes over here. So that is why we got this kind of instantaneous phase image at the bottom on the right side. So the continuity is actually improved on these sides and also these sides, but the real reflector is actually embedded. So we cannot see which one is the real reflector, because every continuity ataupun every trace is actually has the same continuity. Uh, However, we can use this instantaneous phase as a guideline ataupun as a guideline in guiding horizons and fault picking that cannot be interpreted as shown on the above image, particularly on these sides and also on these sides. Okay, we just continue to draw the horizons at these sites based on the informations we got from this instantaneous phase diagram or sections. Next, we have phase coherence. So phase coherence is a common seismic attribute that we always practice or apply, that measure the similarity of the phase of the seismic wave at different traces. So we will look at a particular ataupun at single trace for the phase coherence. So this is very useful tools for identifying structural and stratigraphic discontinuity, such as fault, fractures, and channel edge. So how phase coherence can identify ataupun can highlight the discontinuity such as faults. So faults are often characterized by high coherence value. This is because the seismic wave are reflected of the fault plane, and reflected wave are very similar at different trace. And then we can use the phase coherence to identify fractures, where it can be characterized by high coherence value. However, fractures are typically narrower than faults, and therefore the high coherence value associated with fractures are typically more linear than the high coherence value associated with fault. And finally, we can use coherence phase to identify channel edge. So channel edge are often characterized by high coherence value. This is because the seismic wave are reflected of the channel edges, and the reflected wave are very similar at different traces. So phase coherence is a powerful tool for identifying structural and stratigraphic discontinuity in seismic data, and it's quite common and widely used in seismic interpretation for oil and gas exploration particularly. So we will discuss more further phase coherence in a specific chapter in the next lecture. Next, we have phase curvature. So curvature is a kind of seismic attribute that measure the rate of change of a seismic horizon. So it is a useful tool for identifying structure features such as fault. Okay, most of the time we look on the faults is either anticline or syncline, and faults, and also channel edge. Curvature value can be positive or negative. So a positive curvature value indicates that the seismic horizon is convex, which is represents anticline features, while negative curvature value indicates that the seismic horizon is concave, that represents the syncline type of structure features. Example of how curvature can be used in seismic interpretations. Number one, identifying fault. Faults are also characterized by high curvature value. However, the curvature value associated with fault are typically more linear than curvature values associated with fault. But not just for the fault, we also can actually identify the locations of flat horizon or dipping horizon, where it will indicate in term of zero curvature attributes. And next, we also can identify faults. Faults are often characterized by high curvature value. This is because the seismic horizon is typically folded or distorted near a fault. And then we can also use to identify channel. So channel edge are often characterized by high curvature values because the seismic horizons typically change deep abruptly at a channel edge. Now we come to the end of the lecture. Actually, we will have a dedicated sessions to discuss the fundamentals and also the applications of the coherence and curvature in seismic visualizations. And with that, I would like to thank you for your patience with my unavailability to attend the class this weekend. I hope that you have found this pre-recorded video beneficial. Again, thank you and have a nice day ahead.